Okay, good afternoon, everyone, and welcome to the Physics Colloquium series as a part of the PAR Symposium. And today we have a distinguished speaker, Dr. Kaushik Biswas, and he is from SRNL, which is Savannah River National Laboratory. Dr. Kaushik received his PhD in physics from Texas Tech Lubbock University. After working as a postdoctoral associate at the National Renewable Energy Lab and the Oak Ridge National Lab, he joined Arkansas State University, Jonesboro. Here, he is continuing his work in the field of computational materials, primary semiconductors, and insulators for optoelectronic applications. Thank you so much, Dr. Biswas, for your time, and we appreciate your time. And here you go. The floor is yours, and thank you so much again.
All right, so thank you, everyone. One small correction. I am from Arkansas State University, but if Martine is here and she's listening, I'd love to be part of SRNL anytime.
Oh,
I'm, I'm, I'm not at SRNL, but
oh, so thank you for correcting me.
yeah, no, but I'd love to be there. But I am currently a faculty member at Arkansas State University, and uh, if you can see the slide, I'm awfully proud of my creation, a made-up journal. As you can see, it's a made-up thing, Light Emitters Bulletin, but it's completely made up, just so you know. Don't try to send your manuscript in this journal. It doesn't exist. So we'll talk about although the title says carrier self-trapping and luminescence in intrinsically, it's a long title, in intrinsically activated scintillator cesium hafnium chloride. We will go a little bit sideways too. We will talk about a few other halides as well, because halides in general, and if you look at the literature in the last however many years, you'll see halides occupy a prominent position in the material space because of their chemistry and their very interesting properties. So we will talk about some other halides too, but within the context of luminescence, especially for scintillator applications. And then, of course, we will talk about cesium hafnium chloride also. So, and I am not timing myself. I have the tendency to go over, but it's about 12:35. I will stop just about 45 minutes from now. A little bit of my background. I started off as an experimentalist, as many of you, I'm sure, are. That's during my graduate student days. That was long, many years ago, long time ago. Um, but I soon realized I wasn't very good at it. So I moved into computational study of materials. My PhD thesis was on thermoelectric materials. And my thesis was also on that topic. And once I finished my PhD from Texas Tech, I went to National Renewable Energy Lab, NREL, for my postdoctoral work. I stayed there 3 years, and then you can work your time back. So that would be 2007 to 2010. Then I joined Oak Ridge National Lab, where I spent 2010 till 2012, and then I finally found my faculty position at Arkansas State in 2012, and then I have been here from until then. It's been a long time. It's been a fun journey so far. So now let's get into some of the interesting topics, halide materials that I wanted to talk about. So you are familiar with perovskite halides. They are extremely prominent these days, and many people are working and looking at them for many different kinds of applications. So let's start with that perovskite halide, and on the top you see perovskite halide derivatives. What I mean by that is it's not a subset, a large family of materials that can be linked to the perovskite halides, which we typically talk about right there. If you can see my underlining there. So those are the, we'll say, ABX3 compounds as the perovskite halides. They do not always have the perfect perovskite structure, but we lump them together in as long as they have a cubic structure or close to cubic structure, we lump them together as perovskite halides, and then derivatives that could be 216. Cesium hafnium chloride is an example of that. Then we have other, you see the diversity, the variety of structures. Here we have layered structures right there. Here we call them dimers. Dimers means these octahedral. All of them, the common thing among all perovskites and derivatives is this central atom and the octahedron with halogen atoms occupying the octahedral corners. So let's call them HfCl6 octahedra for the case of hafnium chloride. Hafnium will be at the center right there, and surrounded by 6 chlorine atoms. All of these compounds have that octahedral component as common to them. But then in this type of structure, you see 2 octahedra are sharing faces. And here the octahedra are not sharing faces, but they are forming layers. And here this one is the well-known double perovskite or El Pasolite structure. Where you have 2 different types of octahedra. So there is such a variety in structures, and with differences in structure, you have differences in properties, electronic properties and other physical properties, and that lands them in a very interesting material space. And not just perovskites. I told you we'll go a little sideways and talk about other types of halides. So there are other types of halides too. For example, if we are talking about scintillators, this is another interesting material, cesium barium iodide. Hold on, let me. I don't know if you hear it. My phone is beeping. Let me mute it. I'm sorry about that. So cesium barium, this is not a perovskite structure. It doesn't have those octahedral components to it. It has a complex structure. I think it's a monoclinic structure. But anyway, these are still halides, and they have this halide chemistry, and they are really interesting. And as you can see, this is a pretty important scintillator material when doped with europium. So we will talk a little bit about these types of compounds and then get back to our original material, cesium hafnium chloride, and then we'll be done. So like I said, we do computational materials, which is based on density functional theory most of the time. And typically what we do, we start with a host crystal structure, and then we optimize the structure, and then we can look up, investigate the stability of those crystals versus, one compound, but then there are always other possible secondary phases. And when we grow a crystal, it's very important to have them pure crystals, and that's why their formation energy and their stability versus other competing phases is important. We can look into those, and then obviously we can look into the electronic properties and optical properties of these host crystals. And then thinking or looking at it from the perspective of scintillators, and so we can look at them as self-activated, crystals versus activated. Self-activated means you do not have to intentionally dope them with anything. They can luminesce on their own, meaning the host crystals, whereas others need an activator or a dopant which acts as the luminescence center. And how they act as a luminescence center, how good they would be as an activator, we can look at all those things. For example, in the I just talked about cesium barium iodide, CsBa2i5, that needs to be doped with europium or activated with europium, and we can look at their properties through our methods. So let's start with cesium barium iodide, just a little bit, not too much about this material. It is an interesting scintillator material, and it has to be, like I said, activated or doped with europium. So think of the, like I said, we always start with the structure of the host crystal. In this case, it's cesium barium iodide. It's a complex structure. It's a monoclinic structure, which of course is probably from a crystal grower point of view, they are not easy to grow compared to, let's say, nice cubic structures. In any case, sometimes the difficulty in growing can overweigh the beneficial properties in terms of scintillation that they might have. So it's always a balancing process. There is always some trade-off involved. So they have beneficial properties in terms of cesium, in terms of scintillation. So they're still grown and being investigated. I'm not exactly sure about their current status, but this is from a few years ago. They were being very closely researched and investigated for scintillation. Anyway, in this structure, the interesting thing is the barium site, the site right there. There are two crystallographic sites, two distinct different crystallographic sites where barium can be located. Well, let's call them barium 7 versus barium 8. I say it like that because in one site it's coordinated with 7 chlorine atoms, not chlorine, sorry, iodine. The halogen is the iodine atom. At one side, it's coordinated with 7 nearest iodine atoms, so we call them B7 site or barium 7 site, and the other is coordinated with 8, and we call them B8 or barium 8. What we found through our work is that europium prefers the 7 site. I don't say the barium 8 here. I would say barium 8 as such. Now we found that the europium prefers the barium 8, barium 7 site, sorry, not the 8 site. Why? Because there are chemical reasons. Europium wants to be most comfortable, right? In the lattice, it finds this location to be most comfortable, and therefore it prefers that site. And not only that, it not only prefers that site, we also found that in this material, after you dope with europium, and the europium starts to cluster, meaning it starts to form small domains where you have some europium rich region versus europium poor region, which is obviously not good. You want your activator to be uniformly distributed throughout the crystal. So we found those two things to happen, and that is little bit of a difficulty in terms of don't want them for efficient scintillation. So, and if you are wondering about this, these are the density of states on this side. You see them after you dope with europium. Europium has this right here. These are the half-filled F states of europium, and the remaining of the F states will be higher up in the conduction band, right somewhere there. So when you dope with europium, that's what it does. It is supposed to do. When it works like that, then we say europium is an efficient activator. Europium should create a half-filled state right there, and europium D states should be somewhere right there, and then that creates the situation where you can have DF transition and luminescence. So those are the things that are shown in there. But coming back to this problem of europium preferring the B7 side or the 7 coordinated side, and europium preferring to form clusters or europium rich regions and europium poor regions within the crystal, which will be a problem. In order to circumvent that problem, what we said is that why not try something like this, a quaternary alloy where you have cesium, barium, strontium iodide. You grow the crystal as a mixed crystal like that with barium and strontium instead of pure cesium strontium iodide. People have grown that, or instead of pure barium iodide, people have grown that too. We said, why not try do that in order to circumvent the problem of clustering and europium preferring the B7 side. What is the you may ask, what is the problem here? Why not go with cesium strontium iodide? There is a little bit of a problem because here you see europium will occupy the 8 coordinated side, also the 7 coordinated side. It does not have any preference. It will go if it occupies both of those sides, you have europium F state there and europium F state there, which are energetically, the location of those two different europium states are energetically slightly different from each other. When you have two different europium F states, energetically are slightly different inside the band gap of the host crystal, then you may also run into some problem with the emission properties because there will be different wavelengths of emission for those two types of europium. So that could be a problem. And then of course clustering could be a problem in the cesium barium compound. That's why we said when you create an alloy or a mixed crystal of cesium barium strontium, you do not have that problem. You still have you have strontium and europium occupying the strontium site and just the strontium site. So you have just one europium F state inside the band gap, and you also do not have the problem of clustering anymore. So that was our work. I am not 100% sure where the literature is with respect to that. As you can see at the bottom, these papers are pretty old, from several years back. But that was the work that we did, and these are certainly interesting materials. And then we followed up this work with saying that what if we remove or replace the cesium with Ns2 compounds. Ns2, not compounds, Ns2 atoms. Ns2 atoms would be, for example, gallium or indium or thallium, so on. Even tin, but tin is probably not very useful in this case. So we looked at, just from curiosity a point of view, we said let's replace the cesium and try out some NS2 compounds. Why NS2, you may ask? Because NS2 compounds have this lone pair electrons, those S2 electrons, the lone pair, and this lone pair chemistry is also very interesting. They do not always take part in chemical bonding, but sometimes they do, sometimes they don't, and that gives rise to some interesting properties, and that's the reason we tried out the NS2 atoms. So what we did is instead of cesium, we are now looking at, let's say, indium barium iodide or thallium barium iodide, replacing the cesium with a thallium or an indium. These materials exist. We found them to be stable. Again, the structures are similar as cesium barium iodide, monoclinic structures. So you have two kinds of site, one 7 coordinated, one 8 coordinated. Let's call them B1, B2, or B8, B7, whatever way you want to call them. Just that those two distinct sites are there for barium. And then we did all these sets of different compounds with different Ns2 atoms and comparing with our original cesium barium iodide right there. And if you look at their band gaps, the band gaps are slightly less, not a whole lot, but still some difference, slightly lesser than cesium barium iodide. Cesium barium iodide has the highest band gap here, and smaller band gap is also beneficial in terms of how many electron hole pairs you can create and how many, and therefore how many of them emit, how many of them recombine and give you light. So smaller band gap is not a bad characteristic. But then there are, obviously we are missing cesium now. We have these Ns2 atoms, and therefore the electronic structure looks different. For example, in case of indium barium iodide, you have indium S states right there near the bottom of the valence band, and near the top of the conduction band, you have indium P states. In case of thallium, you have thallium P states right there, and then mostly iodine P states will be here. In this case also you have iodine P states. In indium barium iodide, the top of the valence band will be mostly iodine halogen states, halogen P states. However, in case of indium, you also have some mixture of indium A states as well. In case of thallium, you have mostly iodine P states near the top of the valence band right there, and thallium P states near the bottom of the conduction band right there. And you can compare that with cesium barium iodide. You see there are differences in the electronic structure and also in the band gap. Now let's see what happens with that. So instead, you see in case of cesium barium iodide, what you do, dope with europium. Europium would create a F state right there, and then europium D and barium D would be right there, and then emission will happen between those two. We don't have such a situation in this our new Ns2 compounds. So what will happen there? First of all, let's see if we can dope them with europium. Europium is a very common activator among scintillators. So let's see if we can dope them. Looks like if we do, europium will create the half-filled F states in the middle of the gap, which is fine, which is what we want. There are more requirements. It's just one requirement. There are other things, there are other details that need to be looked into. But anyway, the broadly half-filled europium F states created inside the band gap is fine. That is what we need for europium to act like an activator in these Ns2 compounds, just like we have here in cesium barium iodide. However, there is some difference also. The difference I'll point out in this example on this slide. In the Ns2 compound, so let's take indium barium iodide as an example of Ns2 compound, and this is cesium barium iodide. Cesium barium iodide, you see you have europium F state right there in the middle of the gap, europium D near the bottom of the conduction band. And that is exactly the scenario we need for europium 5D4F emission, which is true in case of cesium barium iodide. However, in these NS2 compounds, we have some problem. The bottom of the conduction band has indium P character, not europium D character. If you dope indium barium iodide with europium, you will have europium F in the middle of the gap. However, europium D will end up near the top of the conduction band, not the bottom of the conduction band. The bottom of the conduction band has indium P character. That is going to be a problem if you are looking for DF transition. You won't have that transition. So that's why we concluded that europium may not be a very efficient activator in case of our NS2 compounds. That's okay. So europium is not an activator. There we could look for other activators that could work well for these compounds, or we can look for self-activation. Is that going to happen? We did some more digging with some more work on these NS2 compounds, and we found that indeed they might be. This is just at that time just our prediction that you may not need an activator. You do not need an external activator to dope these NS2 compounds. They might just luminous by themselves, meaning they might be self-activated. How so? We found for the thallium compound, for example, thallium barium iodide, for example, we found that they can create a thallium bound exciton. What do I mean by that? For an exciton, you need an electron hole localized pair, right? That's an exciton, generally speaking. What we found is that the thallium can trap an electron like so, and at the thallium P state, and a hole can be trapped at an adjacent iodine, in not just one iodine. It's like a VK center. VK center means two iodine atoms come close to create a VK center. That is the hole trapping. You see that normally two iodine atoms are separated by 4 point that distance right there. But then when a hole is trapped, they capture a hole, those two iodine atoms, and they shorten their bond length like so. From 4.12 to 3 point, now I can't read it, 3 point something, 3.19 or so. They shorten their bond length, they create, it's like a I2 minus a molecular ion, if you will. That's famously called a VK center. So the VK center will have the trapped hole. The electron will be trapped at neighboring thallium P site, and those two together will create that bound exciton, and that bound exciton is now able to recombine to give us an emission wavelength of 477 meter or 2.6 electron volt. That was our prediction. Similarly, you can have a similar situation in the case of indium. In case of indium, the whole state or the captured whole state, the localized whole state is slightly different. It's not the VK center, but in any case, we found that you can have an indium bound exciton, and again you can have transition between indium 5P and indium 5S with the emission wavelength of about 2.06. 2.06 versus 2.6, not to be confused. Those numbers, absolute numbers, are not very meaningful. What is more meaningful from our predictive work is that in these NS2 compounds, if they can be grown as pure stable crystals, we do not need to have them doped with an activator. They might be able to luminous by themselves, by their own, according to these self-activation ways, by creating these excitons and emitting at these roughly when again our calculations are not that accurate that these numbers should be taken as granted, but roughly at those emission wavelengths. That was our prediction. Then we went off to our own way, and then we waited. When we do these kind of predictions, we hope that somebody will work on these and try to grow these crystals, and hopefully some of our predictions will come out to be true. So we don't know that. We did not know that yet at that time when we did this work, but we'll come back to it a little later. Now let's talk about cesium hafnium chloride. Not just chloride, I have the other bromide and iodide also. We'll talk briefly about them, but mainly cesium hafnium chloride. You see, if you recall that initial slide, the perovskite derivatives that I was talking about, this cesium hafnium chloride can be thought of as a perovskite derivative, meaning it belongs to that larger family of halide materials that are linked to halide perovskites. Anyway, the structure is cubic, nice and cubic structure. You see these HfCl6 octahedra right there, hafnium at the center and chlorine at the 8 corners. And these octahedra, although the picture looks like this, you have to remember or pay attention, these octahedra are not connected to each other. In a normal perovskite halide, the octahedra would be connected through their corners or through their edges and so on. But in this particular structure, the octahedra are, we call them isolated, meaning they're not connected to each other through their corners or through their sides or through their faces or anything. Obviously, it's a crystal, they are all bonded together. The bond is between the intervening cesium. These cesiums are in those cubo-octahedral, we say cubo-octahedral cavities. These cesium atoms have 12 chlorine atoms from different octahedra surrounding them. So the octahedra are linked with the other octahedra not directly, but through bridged by these intervening cesium atoms. So that's why sometimes they are also called 0D structure, zero-dimensional structure or zero-dimensional perovskites. Sometimes they are mentioned like that in the literature. Why? Because the octahedra are isolated from each other. They're not connected to each other. So that's a little bit detail about the structure. Now we did, again, we start with the structure, we optimize the structure, make sure we have the geometry with the lowest energy possible, and then we call it an optimized geometry. And once we have that optimized geometry, we are ready to look into the electronic structure of these materials. For example, this would be the electronic band structure, which gives us a band gap of about, at the gamma point, the band gap is about 6.3 electron volt, which is the fundamental gap is little bit less than that. So the fundamental gap would be indirect, and it would be, let's say, 6.32. Okay, but at the gamma point, the gap is. But the interesting thing to notice is the flat nature of these band edges. The band edges are important in any material. The band edges tell you how the charge carriers will behave. You see the bands at the edge, this would be the valence band, top of the valence band, and this will be the bottom of the conduction band. And you notice they are so flat. Now, if you look at the density of states right there, just a little bit more detail. Again, you can see the nature of the states near the, again, we are always very interested near the band edges, near the top of the valence band and near the bottom of the conduction band. The top of the valence band, you will see chlorine states right there. Okay, right there, right there. These are same density of states in two different types of calculation, one including spin orbit coupling, the other without spin orbit coupling. Spin orbit, you have hafnium there, a heavy metal, so spin orbit coupling is maybe important, and it's important to include it. So that's why we did both types of calculation. The other is the bottom of the conduction band, which is right there, is made up of hafnium D states. Now, if you go a little bit deeper, if you dig into it a little bit deeper, you will see those hafnium D states are actually split into these D states, what we call the T2G levels, and these are the EG levels. This comes from symmetry considerations. D levels, you have three degenerate T2G levels right there, and two degenerate EG levels. Why do they act like that? Because of the octahedral crystal field. You see, go back to this. This is the octahedra. This is the crystal field created. Under that crystal field, D levels are seen to split like so. The lower energy T2G levels create the bottom of the conduction band, and the higher energy EG levels are in the higher conduction bands. So those are the details, but it's important to notice those things and check your calculations that indeed those are the cases. And also, like I said, since we have hafnium, it's also important to include spin orbit coupling. Although in our calculation, we saw spin orbit effects were there, but not it did not create a very big difference. So without spin orbit, the calculations would also be pretty accurate. Anyway, then let's talk about zirconium. Why talk about zirconium? This is zirconium in CHC, because zirconium is could be an unintentional impurity. Zirconium and hafnium are like brothers. Okay, they are chemically very similar. I think their ionic radius is also very similar. If they are, and they also form very similar chemical compounds. Because of all those kinds of similarity, if you grow cesium hafnium chloride, there is a very good chance that there is zirconium there, and you cannot easily take them out. Because hafnium and zirconium are so similar to each other, you will not be able to easily remove or purify CHC by removing zirconium. So that could be a problem, and that is indeed a potential problem. So we looked at zirconium. You see, when we do calculations, we can do under the perfect of circumstances, right? When we build up our crystal, we can build a perfect CHC crystal with no zirconium at all. But that's not the practical case. Experimentalists will encounter zirconium. So that's why we looked at the effects of zirconium. And what you see here, we call it a chemical potential diagram. I'll not go into too much detail about this, but the importance of this chemical potential diagram is that it gives you the region in the phase diagram. This is not in the sense of a phase diagram that experimentalist, this is the stability region. So I shouldn't call it a phase diagram, but it is like the stability region of cesium hafnium chloride with respect to other competing phases, for example, hafnium chloride or cesium chloride and so on. And when you are considering zirconium, you also need to include the compounds that zirconium can form, like zirconium chloride. So you have to take all of those competing phases into consideration, and then isolate the region in chemical potential space where cesium hafnium chloride will be stable against those competing phases. So if you can somehow, it is not trivial, it is not easy to do, but experimentally, if you can somehow confine to these chemical potential ranges, it is a very good chance that you will be able to grow pure cesium hafnium chloride. So that's the point of figuring this out. And then on the electronic side, we indeed saw when we add a little bit of zirconium to the crystal, it shows up as zirconium D states near the bottom of the conduction band, right there. We have hafnium normally at the bottom of the conduction band, right there, and zirconium also is pretty much appears along with the hafnium D states at a very similar energy. So it behaves almost as hafnium. And so that's what we found. That means zirconium will be there and it will be mixed up with hafnium states like we see here. And therefore, there could be some zirconium related emission as well. You see in this self-activated material, we have hafnium related emission centers. And since zirconium can be an unintentional impurity, zirconium can also become part of that. But it will have a separate emission wavelength because it's zirconium, it's not hafnium. So there will be different, at least two different types of emissions because of this impurity. So then we went on to find out those emission center, what is the mechanism, how does that emission can happen, and for that we isolated different structures. We call them STE1. STE means self-trapped exciton, an exciton that traps by itself. And remember, what is an exciton? It's a trapped hole and a neighboring or a nearby trapped electron together forming the self-trapped exciton. We found at least three different types of structures. And we can find out their binding energy, meaning how stable they are. We found that STE1 is the most stable, STE2 is next, and STE3 is not very stable. When we see these kind of values, these are in electron volts, 0.01, if you take into account the accuracy of our calculations, we can say that STE3 is unlikely to be stable. Under thermal conditions, they will dissociate. But STE1 and STE2 has enough binding energy to stay even under normal conditions to be stable. And then we found out I won't go into the details of their structure, but we found out their emission wavelengths or emission energies for STE1 and STE2 as well as STE3, although we know STE3 is not very important because they will not form under normal circumstances. And the important thing is, again, we know how accurate our calculations are. So when we see these kind of numbers, 2.96 versus 3.06, we say that both self-trapped excitons have very similar, if not exactly similar, very similar emission energy. So you won't be able to tell one from the other. They are pretty much, they emit at the same wavelength or same energy. And they also have very similar binding energies as well. And then for the case of zirconium, we found out different emission energy of 2.37. And the zirconium is also stable. You see, STE1, it also forms similar structures like STE1 and STE2. And they're also stable, and their emission energies are also very similar. However, from hafnium STEs versus zirconium STEs, the numbers are different. Okay, so like it matches up with what Arnold Berger and their collaborators did back in 2015. They found out that There is the principal decay time and a principal emission wavelength of, where is it? Right there, 400 nanometer. That 400 nanometer corresponds well with these two numbers right there. And I'm making a mess of my own slide, I know that, but that's how I do it. And so it corresponds very well with the hafnium related STE1 or STE2. So we thought that this could be the self-trapped mechanism of this self-activated scintillator. But not only that, they also found, I don't mention it here for some reason I forgot, they also found another emission wavelength which corresponds well with to this value, around 480 nanometer or so. I am not exactly sure. They also found a second emission wavelength around 480 or so. I think 480 corresponds well with that, and we identified that, or at least based on our calculations, uh, we could say that that could be zirconium impurity related emission that they found. So that's what we did with the cesium hafnium chloride, just sort of figuring out the material, understanding their electronic properties, and figuring out their emission mechanisms for this self-activated material. How those self-trapped excitons are formed and how they emit. And then we can skip this. There, you see, when you can have cesium hafnium chloride, you can most likely you can also grow bromides and iodides, and when you do that, your bromides and iodides will have smaller wavelength, not smaller wavelength, smaller band gap compared to cesium hafnium chloride. Okay, so, and that's not bad. We need smaller, like I said, smaller band gap often translates to better emission. And so we looked into that, and I think people eventually also tried growing those crystals, and especially maybe mixed crystals like that, where you have a little bit of chloride bromide mixed in, and things like that. So I again defer you to the most current literature on these other types of materials, including the mixed halides in this series of cesium hafnium halide group of materials. So I am pretty much at the end of my talk, and I will not talk about this. There you can see we can do a lot of other types of calculations for other types of materials. Um, so conclusions, like I said, different types of materials have different ways of emission, and we want to figure out and understand those emissions and make them more efficient. In cesium barium iodide, like we said, a mixed quaternary or a mixed halide of cesium barium strontium iodide probably would be a better would give better results. But anyway, this in itself is a good material with EU DF transitions happening like so. For the NS2 compounds, like I said, we do not need europium doping. They most likely can be self-activated and emit and be able to emit. And not only that, we saw that after our work, I think they were followed up by experimental investigations, especially I think this material, thallium strontium iodide, which some of those materials were confirmed and found to be luminescent without any doping. So that was a good result for us in the where we predicted first and experimental result followed. And then obviously cesium hafnium chloride, where is a good example where experiment came first, followed by our computational work or theory work, trying to explain the experimental observations. And that's that. And finally, more conclusions. I will leave it up there, and I'll finish my talk right here.
Thank you
Thank you
so much,
so much.
Dr. Biswas. It was very detailed, and I'm sure you need a bottle of water right now. So now it is the opportunity for the attendees to see if you have any questions, and feel free to, get some insight in more details of if you have any questions. But
Okay.
so somebody has their hand raised up, I think, but I'm not sure. Okay, Jonathan Baker.
Hi, great talk. I'm also a computational materials scientist. I was wondering on the polaron and exciton simulations, did these self-trapping distortions stabilize themselves, or did you have to perturb it randomly to get it to start relaxing to that?
Oh yeah, you have to do it a little bit. You have to. We have to go into the structure, and like you said, we have to perturb it so that it allows the computer to pick up on that structure and then relax it to the most stable structure. Yeah, you have to play with the bonds, make them a little bigger or make them a little shorter, bring the two chlorine atoms together a little bit, things like that.
Okay, thank you. My experience was similar.
Sam, would you like to go next?
Yeah, sure. Thanks. Sorry I missed first half of your talk. But this was a great talk. I had a question towards the end of the slides. You suggested that as you go down the group, you do get an improve in luminescence of those halides. Do you foresee the same thing also happening with the optical properties as it relates to the um, decay times of those materials?
Um, I wouldn't be able to say that for sure. As a general measure or general comment, we can say that if we have a smaller band gap, that's better for luminescence. But in terms of optical properties, or there are so many variables, you know that, so we won't be able to say that every property or many properties will improve. Some properties may actually get worse when you go down the group.
Okay, thanks.
So that's where our work will help. If we can sort of work, do our calculations, and which takes lesser time than time consuming experiments doing with trying to do with many, then we can give you some ideas, at least, that what iodine may be better suitable than chlorine or vice versa.
Thank you, Dr. Biswas. And we have Dr. Utpal Rai. Dr. Utpal Rai.
Hi, Kaushik. This is Utpal from Savanadiva.
Yes.
This is in connection to your last answer. My question is that for CHC, what is wrong with iodide compared to chloride?
Compared to chloride, I would not, Utpal, I would not be able to tell you, because trust me, I have not followed the literature closely. I am not updated with the most recent CHC related literature. So you probably, is there, I'm sure many groups have tried to grow this, right? Is there any indication, maybe you can tell me a little, is there any indication that the others doesn't work so well as the chloride?
CHC is always best.
Ah. So you see, it's not necessary that when we pick other ions that they might have a smaller band gap, but other properties can get destroyed. So yeah, so experimentally you have seen that, right?
Me, some other people, yeah.
Yeah. Okay. Okay. But that would be a good thing to see what is going wrong with iodide versus chloride. Yeah.
Yeah, theoretically, can you predict by any chance?
We can look. I cannot guarantee what we will find or if we will find anything. We in that paper that we did on cesium hafnium chloride, we just did a very few preliminary calculation on the bromides and iodides just to look up their band gap and some very broad idea. We didn't go beyond that. But if we dig deeper, there is a chance that we might be able to figure something out and at least have some idea why they behave differently and why the iodides behave worse than chlorides. But without getting into and looking at them carefully, I won't be able to tell whether what is wrong with it or if we will find anything from there. But there is a good chance that we would be able to have some ideas.
Thank you, Kaushik.
Any more questions from the floor? Okay, thank you so much, Dr. Biswas. It was very entertaining and informational, and then I'm sure like a lot of us learned a lot of things. Thank you so much again, and I'm going to upload it onto YouTube, and I'm going to share the link with all of you. Thank you so much again, and thank you so much to the audience also for attending this session.
All right, thank you.
All right, okay. Have a good day, all of you.
Thank you.
Bye.